Welcome back to the series on statistics. In this video, we're going to start to talk about sampling distributions. And so if you remember from an earlier video, the difference between a parameter and a statistic as such is that a statistic is a number or measurement that makes a statement about a sample from a population, and a parameter is a number or measurement that makes a statement about the population itself. So the common example is the census in the United States. This is a survey that's done every decade where they go out and they take measurements for every single person in the population, at least in theory. And so these are supposed to be parameters that describe the demography of the United States, not statistics. Now, in contrast, you can imagine that that's a very large undertaking to attempt to do. It's probably not going to be 100%. They're not going to get every single person, but they might get the majority, the vast majority even. But you can imagine situations where this is too much work for what you're trying to accomplish. And you could imagine situations where this might even be impossible. So, for example, if you were trying to record the average speed of some type of particle in a laboratory, it's not going to be possible for you to survey every single one of those particles. And so you're going to wind up having to use statistics to make inferences and statements about these populations. So this is a very important tool that comes from statistics, is the ability to make statements about populations that are based on samples. And so to uncover what kind of statements we're going to be able to make using statistics, let's see what we can discover about the probability distribution for the sampled mean of a population. So that's going to be the focus of this video. Let's see what we can find out about it. All right, so before we officially start here, you're probably going to want to get used to hearing this, but we're going to have some assumptions we need to make. At least these are pretty intuitive. So when you're sampling a population, you want there to be randomness. And so ideally, you want every element of the population to have an equal probability of being chosen. So if you're taking a sample of people at a gym and you're asking them how many minutes a week do you spend exercising, and you decide to use that sample to make a statement about the general population, then you're automatically only sampling people who actually go to the gym, and you're not going to be including people who don't exercise at all. And so that's going to skew the results of your sample. And so if you want to make statements about the entire United States population, for example, that would be a bad way of doing it. And so you have to keep that in mind when you're constructing the methods of sampling populations, is that you want every element in the population to have an equal probability of being chosen. Very frequently, it's more convenient to adjust the statements you're trying to make. So for example, if you were doing that survey that we just talked about, it would be more efficient to say, oh, well, here's how many minutes per average, or how many average minutes per week people who go to this gym exercise. And then that would then become an accurate statement. And then it would be approximately random, the people that you're choosing. The second assumption is that you want independence with your sampling method. So you don't want choosing one element to alter the probability of choosing another. You can see how that could be catastrophic for results of the sample. And so you want both of these assumptions to be in place so that the measurements that you're taking about your sample are actually descriptive of the population itself. All right, so now that we have our assumptions out of the way, let's see what statements we can make about the sampled mean of the population. Let's see what we even mean by that. And so for this, I have a population over here that ranges from x1, x2, all the way up to xn. So there's n elements in this population. And just to make the math easier, I'm going to assume a sample size of 2. And so what kind of samples could we draw from this population? The first one I could think of would be drawing the first element twice. So I sample the population, and I get the first element twice. Now you might be sort of thinking to yourself, well, how could you pick the first element twice after you pick the first element? You're only looking at the remaining elements in the list. You can't pick the same thing twice. But there's a problem with that. And that problem is, if I pick the first element, and we're assuming randomness, we're assuming that every element has an equal probability of being chosen. And there's n elements here, then every element in this list has a 1 in n chance of being chosen. Now, if we don't allow replacement, then after I pick the first one, we're only looking at the remaining elements. Once again, if we assume that every element has an equal probability of being chosen, and now there's only n minus 1 elements, then every element will have a 1 in n minus 1 chance of being chosen. And so, but this is going to violate our independence assumption, which says that choosing one element does not affect the probability of choosing another. And so the only way that we can have a valid sample for this population is if we allow replacement. Now in practice, generally you're looking at sample sizes that are so vast, or populations that are so vast, that sampling that population and getting the same element twice is basically impossible. It's statistically impossible. But in theory, we do need to concede that this is a possibility. Otherwise, our sampling assumptions will be violated. And so that's sort of the only weird example. Outside of that, we have every other, sort of normal combination you could think of. We would have x1, x2. We could have x1, x3, all the way down to x1, xn. And so these would be all the possible combinations we could draw. Technically, we could reverse the order. We could do every single one of these in reverse order. We could draw x2 first, and then we could draw x1. And so I'll just notate that, instead of writing all of that, I'll just notate that by times 2. These are all the possible samples we could draw from this population that involve x1. And then you could think of extending this and sort of creating the same list, but for x2. And so that would start down here. We would have x2, x2. That'd be our first possibility. And then we would have x2, x3, etc., all the way down to x2, xn. And so all of these samples right here, they could be reversed. And so you could have the probability of picking x3, or the possibility of picking x3 and then x2. And so there's times 2 of each of these samples. And so these would be all of the possible samples you could draw that include x2, except for this one, or technically these two, where you draw x1 and x2, or x2 and then x1. And so these are all the possible samples. You can imagine you'd have to continue doing this for every element of the list, all the way down to xn, xn. But if you drew that all out, then you would have every possible sample that you could pull from this population. Every single possible sample of size 2 that you could draw from this population. Now let's talk about what we mean by the sampled mean. It's exactly what it sounds like. The sampled mean is just the mean of the sample. And so if we took this as our sample, x1, x1, then our sample mean would be x1 plus x1 over 2. That's our sampled mean. And here we would get x1 plus x2 over 2. And you can imagine continuing this, etc. And so here you get x2 plus x3 over 2, etc. for all of these elements. This would be our sampled mean given these samples. And so what we're interested in here is this probability distribution for these sampled means. And so in other words, what we want is we want to take this data, the information that is contained in all these sampled means, and we want to see if we could find the average of these sampled means for all possible samples. And we want to see if we can find the standard deviation for the sampled mean given all possible samples as possibilities. And so in this way, we want to construct a probability distribution for the sampled mean of a population. This is what we mean. We're taking into account all these sampled means, every single one of them for every possible sample, and figuring out what the average of those is, what the standard deviation of those is. That's going to be our goal right now. Now let's contend with the mean of these sampled means, so to speak, first. And so let's sort of consider what that would be. So if we wanted to get the mean of all of these sampled means, the average of all these sampled means, we would have to add them all up and divide by how many there are. And so in our denominator, we're going to have the number of possible samples that we have here. And in our numerator, we're going to have the sum of all the sampled means. And so every single one of these sampled means is going to have a denominator of 2, right? I mean, every single one of these samples has a sample size of 2. And so for each one of them, you're adding the 2 elements and then dividing by 2. And so if we wanted to add up every single one of these sampled means, we're essentially adding up every single one of these elements and then dividing that entire series by 2, since there's a common denominator of 2 in every single one of these sampled means. And so the sum of all the sampled means is exactly equivalent to taking the sum of every single one of these elements that we see here. Every single time an x1 appears, we add it all together. Every single time an x2 appears, we add it all together, etc., all the way down the line for xn. We're taking the sum of all of the different elements that appear in this list here, in the list of every single possible sample. And so if we were to take that entire sum and divide it by 2, then we would get the sum of all these sampled means. And so if we took that sum and then we divided it by the number of different possible samples of size 2 that you could pull from this population, then we would have our mean, our average, for the sampled means. And so that's the process that we're going to deal with now. And so just to sort of do that, let's consider how many times does x1 appear in this list of every single possible samples. Well, x1 appears twice in this singular element here where we draw x1 twice. So we have two x1s here, two x1s. And then here, this is every other possible sample of size 2 that you could pull from this population that contains x1. And how many elements are in this list here, just this portion? Well, if you go down the line here, we're starting at x2, and then x3, and then x4, and then we're going all the way down to n. And if you started at 1 and went down to n, there would be n elements. And since we're starting at 2 here, there's n minus 1 elements, n minus 1 elements in this list. But we have to remember that because we're taking into account the possibility of flipping the order for every single one of those, there's really 2 times n minus 1 elements in this list that include x1. And so every single possible sample of size 2 that contains x1 is contained in this list right here. So if we sum up all of these possibilities, we're going to get the total number of times that x1 appears in our list of every single possible sample of size 2 that you could pull from this population. And so if you add these up, we have 2 times n minus 1 x1s. And so what's that going to be? This is going to be 2n minus 2. And then if you add the 2 x1s that appear in this sample right here, we're going to have 2n x minus 1s. Or sorry, 2n x1s. So that's how many of those we're going to have. Now let's consider, what about x2s? So here we have 2 x2s. And then in this list, we're starting at 3 and then we're going down to n. So there's n minus 2 elements in this list. N minus 2 elements. But really, we're doubling this because we're taking into account the possibility of switching this and drawing an x3 first and then drawing an x2, for example, but for all of the possible elements in this list. And so really, it's 2 times n minus 2 x2s that appear in this list. And this column is going to represent every single possible sample of size 2 that we can pull from this population that has an x2 in it. And so we have 2 x2s here, and then we have 2 times n minus 2 x2s. And so if you carry this out, this is 2n minus 4 plus 2 x2s. So there's 2n minus 2 x2s, right? Pause for a minute, maybe think about it. No, it's not right because we're missing 2 x2s. Where are these 2 x2s that we're missing? Well, they're right here. And this is the only element in this list that contains x2. Every other sample in this list of x1s doesn't contain it. But there's a possibility of sampling and drawing x1 and x2, and also the possibility of sampling and drawing x2 and x1. And so there's 2 other possibilities that contain x2 here in this list. So really we need to add 2. And so we're going to get 2n x2s. And so that is our final answer. So we have 2n x1s and we have 2n x2s. And you can imagine here we have 2 possibilities, 2 possible samples that contain x3. And here we also have 2 possibilities that contain x3. And if you were to continue drawing these columns, and you started with x3 at the next one, you would have x3, x3, and then you would go x3, x4, x3, x5, etc. And every single one of those samples that doesn't include x3, x3, you would have to double that. And if you took that number of x3s and then you added these 2, or these 4, I guess, you would get 2n again. And so I encourage you to do that yourself if you don't believe me, but essentially what we're saying is that there's going to be 2n there's going to be 2n elements of every single xi in this list from I is equal to 1 to I is equal to n. So there's 2n of every single one of these elements in the list of every single possible sample of size 2 that you can make from this population. And so why is this going to be useful? Well, this is going to allow us to make the statement that if you sum up the sampled means, and here I'm going to use x bar to denote the sampled means, for every single possible sample that is in this list, this is equivalent to summing up every possible element in this list. And now we can actually do that because that's just going to be 2n. Every single one of these elements appears 2n times, so this is going to be 2n multiplied by, and then you just add up each of the elements in the population. So you have x1 plus x2 plus all the way down to xn. And so this is going to be the sum of all our elements, and then you could think of distributing this 2n across all of them. That will give you the sum of every element in this list. And as we said before, if we want to calculate the sum of all of the sampled means, then we have to divide this sum by 2, because they all have a common denominator of 2. And so if you divide this by 2, what are we going to get? We're going to get that the sum of every single one of these sampled means is going to equal n times x1 plus x2 all the way down to xn. So that's the sum of all our sampled means. And now if we want to calculate the average of our sampled means, or the mu of x bar, which is a very interesting, x bar is the sort of FOIL of mu. It's the mean of a sample. But this is the mu because it takes into account all of the possible samples of size 2 that you could pull from this possibility. So this actually is a parameter, but it's a parameter that's describing statistics. So this is I like this a lot. It's very interesting. But this is going to be given by taking this sum, the sum of all the possible sampled means here, and then dividing by the number of possible sampled means. Well, how many different possible samples do we have here? We could go through and try and figure this out, but it's actually not that complicated. There's n elements in this list, and since we're dealing with permutations here where order matters, and we're dealing with replacement, it's actually very simple. There's n possibilities for the first element that we choose, and then there's n possibilities for the second element that we choose. So there's a total of n squared possible choices. And so the mean here, the mean of all of these sampled means is going to be this sum divided by the number of possible choices, which you just determined is n squared. And so it's going to be n times x1 plus x2 plus x3 all the way down to xn divided by n squared. And so here, these n's are going to cancel, and we're going to get the sum of all of the elements in the population divided by the number of elements in the population. Now that should sound familiar because this is exactly what the mean of the population is. And so we have this interesting dynamic going on where if you take the mean of all of the sampled means, all of the possible sampled means, you're going to get exactly the same mean as the mean of the population. And this is true regardless of your sample size and regardless of your population. If you take the mean of your sampled means for any sample size, for any population, the mean of your sampled means is going to be equal to the mean of your population. So this is just one little example of that. All right, so the next question that we want to contend with is what about the standard deviation or the variance of these sampled means? Now this one is a little bit more challenging to look at. I'm actually not going to do a formal proof of this or anything. I guess I didn't do a formal proof of the last one since I was confined to a sample size of 2. I just wanted it to be easy to understand. So for this, I'm going to look at a very simple population, just the numbers 3, 2, and 1. And I'm going to consider what happens to this population as we start to take sample sizes again of size 2. The first thing I want to look at, though, is what is the mean of the population itself, and what is the standard deviation of the population itself. So if you recall, the mean here is going to be equal to the sum of all of these divided by the number of elements. So we have 3 plus 2 plus 1 is 6 divided by 3. That's just going to be 2. Now, the standard deviation is going to be the sum of all of the differences squared of each of these elements divided by the number of elements. So our standard deviation here, or technically our variance, is going to be the sum of, 3 minus 2 squared plus 2 minus 2 squared plus 1, 1 minus 2 squared, all of that over 3. And so this is going to give us 0 in the middle and then 1 and 1. So we have that our variance is equal to 2/3. And our standard deviation then is going to be equal to the square root of 2/3. And so that's our standard deviation and our mean for our population. Now let's consider what starts to happen when we look at the samples, the possible samples of size 2 that we could make from this population. And so I have a list here. These are all of the possible samples of size 2 that you could pull from this population. Now let's consider what the sampled means we would be if we took the mean of each one of these samples. So here, the average of these 2, 3 and 3, that's obviously just going to be 3. And then we get 3 and 2, that's 5 halves. We get 2 here, 5 halves. We get 2, 3 halves. Here's 2 again. And we have 3 halves again. And then we have 1. And so these are all of the possible sampled means we would get. Now if you took the average of these, you would have 3 plus 2 times 5 halves, so that's 5, so it's going to be 8. Plus 8 plus 3 times 6. I'm very bad at arithmetic in my head, but I'm going to try and do this. This is going to be 14. And then we have 2 times 3 halves, that's 3, so 14 plus 3, that's going to be 17, and then we add 1, we get 18. And how many possible elements are there? We have 9, so 18 over 9, that gives us a mean of 2. So what we found here, that the mean of the sample, all the possible samples of size 2 that you can make from population, this is holding true here. The mean of all of these possible samples is equal to the mean of the population. It's equal to 2. But what about the standard deviation? I think for this, I want to actually construct sort of a faux probability distribution, or a probability distribution. So I have a little table here, and I have all the possible values of the sampled mean that we can take for all of these possible samples of size 2 that we could pull from this population. And I want to associate each one of these with the probability. And so there's 9 total outcomes here. And so we have the probability of getting 1. Well, that only happens once here, so that's going to be 1/9. It's going to be 1/9. And then what about the probability of 3/2? That happens twice. So this probability is going to be 2/9. And that's going to be the same for 5/2. And the same for 3 is going to also have a probability of 1/9. And then 2 here appears 3 times. So this is going to have a probability of 3/9 or 1/3. 1/3. And so now that we have these values of the sample means associated with their probabilities, I'm going to calculate the variance by doing the second moment here, minus the mean squared. And so I'm going to calculate the variance that way. So if you recall, variance is equal to the expected value of of x squared, or the second moment, minus the expected value squared, or the mean squared. And so here, I'll notate the mean of x bar, but just note that this is equal to the mean of the population. And so what's our second moment here? That's going to be each one of these sampled means squared multiplied by its associated probability. So we have 1/9, so that's going to be 1 times 1/9. And then we have 3/2 squared multiplied by 2/9. So that's going to be 9/4 times 2/9. The 9s will cancel, and we'll have 2/4. So that's going to be 1/2. I might not be able to do the rest of these in my head. Like I said, I'm very bad at this on-the-fly arithmetic. This one's easy. That's just 4/3. Maybe I can finish here. It's 25/4 multiplied by 2. So that's going to be 25/2 times 9. That's 25/18. And then here, we're going to get 9 times 1/9. Oh, so that's going to be 1. Perfect. And now we need to subtract off the mean squared. And so that's going to be 2 to the power of 2 is just 4. And so we have, this is our variance. Now we need to find a common factor here. Okay, so let's do this. I guess we'll go to 18. So I don't think this reduces. And so we're going to have 2/18. 2/18 plus 9/18 plus, I need to multiply both by 6, 24/18 plus 25/18 plus 18/18 minus, I'm going to leave that because maybe this will reduce. Okay, so 2 plus 9 is 11. 11 and 24 is 35. 35 and 25 is 60. 60 and 18 is 78. So we have 78/18 minus 4. All right, it looks like I have to do this because I'm not going to bother trying to reduce that. So 18 times 4, we get 32, and we get 72. And so this whole thing winds up reducing to 78 minus 72. That's going to be 6/18, and 6/18 is just 1/3. So that's going to be the variance of our sampled means. And so I can notate that like this. The variance of our sampled means we found was 1/3, and the standard deviation of our sampled means is 1 over the square root of 3. And so the key thing that we want to realize here is this relationship right here between the variance of our sampled probability distribution and the variance of our, here I'm going to move this a little bit and sort of rewrite this just to make this obvious. I want to put these next to each other. And so here, take this and copy it, and move it down to the bottom. This is the point that we want to make. If you take the variance of our population and compare it to the variance of our sampled mean, it's going to differ by a factor of 2. Now that 2 is significant because that 2 was our sample size. And so this is the point that we want to make with this video, is that if you do a sample of a population, if you conduct a sample, then the mean of your sampled means is going to be equal to the mean of your population, and the variance of your sampled means is going to be equal to the variance of your population divided by whatever your sample size is. This is the fact about sampling distributions that we want to point out. What that also means is that the standard deviation of your sampled means is going to be inversely proportional to the square root of your sample size, because you have to keep in mind that it is the variance that is getting divided by a factor of the sample size. I'm going to write this all out so it's a little bit easier to see. And so this is the fact that we want to hone in on here. If a random sample of size n is conducted on a population with a mean of mu and a standard deviation of sigma, then the mean and standard deviation for the distribution of sampled means is as follows. You have the mean of the sampled means will be equal to the mean of the population, exactly the same. But the standard deviation of the sampled means will be equal to the standard deviation of the population divided by the square root of whatever your sample size is. So I hope this video made these a little bit clearer, showed you why they sort of make sense. I know this doesn't suffice to be a formal proof, but I think the formal proofs can get a little bit complicated when you're talking about things that are heavily involved in combinatorics and things like that. And so I decided that this would be a much more intuitive explanation for why we have these properties. But these are the properties that we were interested in showing. And so just to give some sort of a hint as to the direction with which we're going with this, if we were to assume that these distributions for these sampled means were normal distributions, they look something like this, with the standard deviation equal to, and of course this is the distribution for the sampled means. This distribution has a standard deviation of the standard deviation of the population divided by the square root of the sample size. And so if we were to assume that these distributions were normal distributions, then we already know we have the ability to draft probability density functions for these situations. But in addition to that, we also know the general structure of these probability distributions. And so if this were the case, we know that we could increase the sample size, and this would increase this would decrease the standard deviation. So you could get this transformation here by just increasing the sample size. You're decreasing the sample. And you can see that here, by increasing the sample size, we're severely restricting the majority of this data to be much closer to the mean than it was before. And so what is this going to allow us to do? Well, we know certain facts about the normal distribution. For example, we know from the empirical rule that roughly 68% of the data will be within one standard deviation of the mean, roughly 95% of the data will be within 2 standard deviations of the mean, etc. And so what this is going to allow us to do, if these are normal distributions, is to make statements like this. So we'd have a statement that says something like 99.7% of samples of size n will have a mean within 3 times the standard deviation here. This is going to be the sigma divided by the square root of n of the true mean for the population. And so you can imagine if we plugged in some numbers here. So for example, if we were talking about heights, and let's just say that the average height is 69 inches for a United States man, and let's say the standard deviation is 3 inches. I have no idea if these numbers are accurate. I'm making them up. But let's say that this is the case. And let's say that we didn't have time to survey all 150 million men in the United States to ask them what their height is. So we did a sample size of 100. Then what this would allow us to do, if these were normal distributions for these sampled means, then what this would allow us to do is make the statement that 99.7% of samples of size 100 will have a sampled mean, so x bar will be within 3 times the standard deviation divided by the square root of that. So that's going to be 3 over 10. So 3 over 10 is 0.3 inches. And so 99.7% of samples of size n will be within 69 plus 0.3, so 69.3 and 69 or 68.7. And so 99.7% of samples of size 100, if these numbers were true, would be within these bounds. And so you could think that this gives us the tools, because 99.7% of samples having this property is enough to say, okay, I'm fairly confident, I'm very reasonably confident that if I do a sample of the size 100, that it's going to be very close. The mean of that sample is going to be very close to the true mean of the population. Here we're assuming that the true mean is 69, and we got a values for possible standard deviations, values for possible sample means that are ranging within 68.7 to 69.3. Virtually all samples of size 100 would be within this range because we're talking about 99.7% of them. And so if you have a sample of size 100, you could imagine being reasonably confident that its sampled mean, the mean of that sample, will be pretty close to the mean of the population. In fact, roughly this close. We have the bounds here. And so there's obvious problems that come with this. It's just, first of all, this only works if we assume that these distributions for the sampled means are normal distributions. This is the only way we can make statements like this about the distributions, because we have all of the concrete information we could ever need about normal distributions. We derive their probability density functions. We can integrate them and do all sorts of things with them to make all the sorts of statements that we want. But we have no way of knowing that these are normal distributions. Secondly, we have no idea, like if you already know what the standard deviation of the population is, that's a lot of information that you're assuming. So we're going to deal with both of these problems. This is sort of the structure of the rest of the course. First of all, we're going to have to discuss moment-generating functions in the next video, because that is necessary information that's going to have to come before we prove the central limit theorem. The central limit theorem tells us that as we increase our sample size, this distribution for for sampled means is going to become approximately normal. In fact, if you take the limit as the sample size goes to infinity, the distribution for the sampled means becomes exactly the same as the distribution of a normal distribution. This is what we sort of hinted at in the last video. We're going to talk a lot more in depth when we cover the central limit theorem. But generally, we're not interested in infinite-sized sample size, because obviously that is just exactly the same as sampling the entire population. Even worse. Essentially, what we're saying is that at a certain point, it becomes negligible, the difference between the distribution of the sampled means and a normal distribution. So at a certain point, the cutoff tends to be around a sample size of 30. That's what they say. There becomes a point where you can use the properties of the normal distribution to make statements about your distribution of sampled means, and you could be reasonably accurate. And second of all, this problem of having to have a standard deviation for your population in place, we're going to deal with that. We're going to talk about t distributions, and we're going to talk about t-scores, t-testing. That's going to be how we're dealing with that. But all of this is just a structure for what is to come. Don't worry if that's a little bit overwhelming at this point. The next thing that's going to have to happen is we're going to have to talk about moment-generating functions to prep for the central limit theorem. So I hope that sounds interesting. I hope you guys enjoyed. Thank you all for watching. I'll see you in the next one.